I'm going to use an analog of a magnetic circuit. This is an iron ring, and it carries two coils, a large primary coil and a smaller secondary coil connected to an ammeter. When I switch a current from a battery into the primary coil, there will be a momentary current in the secondary. I'm going to remove the meter and replace it across the secondary with a small lamp. If now I can change the current in this coil continuously, which I can do by feeding it with alternating current, then I can light the lamp continuously. It seems as if the iron ring is acting as a sort of transmitter of something or other between this coil and that one. And we call this something a magnetic flux. Now let's see what will happen if we take the iron ring away entirely. Now with the secondary coil in the same position as before, I switch on the AC as before, and now the lamp does not light. Now this magnetic circuit is not quite the same as the electric circuit. Let's see what happens if I put the iron back, but keep a gap in the circuit. Now it looks as if we've broken the circuit completely. Nevertheless, when I put on the coil and switch on the AC, we light the lamp, even though it's not as bright as it was before. So it seems that our magnetic flux can jump this gap, and that air itself is a conductor of magnetism, even though a weak one. Even if we take the iron away entirely, there would still be an effect, even though it wouldn't be enough to light the lamp. Now let's apply these findings to our permanent magnet systems, looking at the permanent magnet in a quite different way. On this board, I've drawn out the lines of force as they would appear from a bar magnet there. But I've drawn them out in electric wire, because instead of a source of magnetomotive force, I'm going to use a battery, which is a source of electromotive force. I'm going to measure the current flow in these lines on this meter. When I switch on the battery, we're now measuring the current in all the wires together. Now remember that air is a bad conductor of magnetism, so these are high resistance wires. In this context, steel would be a good conductor, so it's represented by this piece of copper. When I put the copper down on the wires, the current increases because I'm short-circuiting some of the high resistance parts. And as I slide it round towards the pole, I'm covering more and more wires, so the current continues to increase. The law of nature is such that it will always try to reduce the reluctance of the external circuit. And this is the rule we shall now use in place of the rule of magnetic poles. And we can use it to explain all the phenomena of magnets which we saw earlier.